I'm a science fiction fan, and I've long felt that this agency ought to be on our way to the stars. So, and we are. But I think some of the things you're going to hear today may get us there a lot faster. So this is, our, I think it's the penultimate talk in the summer series. This is a series to celebrate NASA Ames 75th anniversary. By the way, at the picnic the other day, I met a fellow that started working here right after we were founded in 1940, so really cool. So Ames is good for your health. That doesn't work statistically, I think. But today we have Dr. Harold Sonny White is our guest. He holds a PhD in physics from Rice University, a Master of Science in Mechanical Engineering from Wichita State University, and a Bachelor of Science in Mechanical Engineering from the University of South Alabama. He currently serves as the Advanced Propulsion Theme Lead for the NASA Engineering Directorate and is the JSC representative to the Nuclear Systems Working Group. Kind of cool stuff. He is serving to help the agency incorporate high TRL advanced power and propulsion technologies into near and midterm human exploration architectures. But he's also pursuing theoretical and laboratory research on developing lower TRL advanced propulsion and power technologies in the Advanced Propulsion Physics Laboratory known as Eagleworks that is located at the Johnson Space Center, which I'm on my way to this afternoon, where it's 98 degrees when I looked at and the humidity I think is about the same, so be glad you're in California. Oh, by the way, before I go on, tomorrow is a talk on a lot less fun topic, but one you all need to know is about export control. So I do urge all the staff to be here. Chuck Duff, you'll be taking, attendance. I particularly want the managers to be here. I got in trouble over that stuff a few years ago, so we're going to do a lot better. But without further ado, let me say hello to my friend and my colleague, Sonny White from Johnson Space Center. The stage is yours.
Thanks, Pete. Appreciate it. Thank you, everybody. Thanks for coming to join me today. As part of coming into this series, I was asked to maybe talk a little bit about what got me into working the space industry. What was some of the background that inspired me. I grew up in Washington, D.C., just outside of D.C. in Virginia, and spent quite a bit of time going to the Air and Space Smithsonian in D.C., and I was really inspired by all of the displays that they had there of the Apollo program, a lot of the aircraft. So I think I got the bug at a very early age to want to get into the space program. So it was quite a treat to be able to eventually find my way working at NASA on human spaceflight back in 2000. And so hopefully we'll have a lot of years in the future to try and contribute to the cause that we all kind of care about in terms of trying to go and explore and figure out some new things. Just a little bit of background on some of the stuff that I do that's a little bit higher in the TRL. Pete talked about the fact that I do work with some higher TRL stuff. I've done some work with trying to integrate things like Hall thrusters into human spaceflight, and so you see a little a montage of some of the projects I worked over the last couple years trying to integrate things like Hall thrusters into human spaceflight platforms. You see on the top left there, the International Space Station, we looked at using Hall thrusters to provide some drag makeup, so we spent some time trying to figure out how to integrate those onto the space station. Typically in human spaceflight, we always think of rockets that have nozzles and they make a lot of smoke and a lot of noise and have a thrust-weight ratio greater than 1. So it took a little bit of time and effort to help people overcome the perspective that low thrust might not necessarily be something that we can use, but it turns out it really can help with human space exploration. And so we looked at several other things about using low thrust in space propulsion systems. On the bottom right, you see a concept that looked at trying to use Hall thrusters with some assets in the Earth-Moon Lagrange point area. This was kind of a precursor to the asteroid mission. And we also did some work with DARPA to kind of think about ways that we might be able to do some collaborative efforts. But these are all concepts that try and address getting out of low Earth orbit into cis-translunar space, maybe one day out to Mars. It's at 1.5 AU. But what if we want to go through and explore the rest of the solar system? What if we want to get out to some other locations with people in the outer solar system? What if we really want to try and go to some place that's even further, some type of an interstellar destination? I think you have a talk on Kepler in a couple of days. And Kepler is identifying a lot of very neat things that are out there, and we're finding out that there's a lot of planets out there. And our solar system is not unique from the standpoint that it has bodies that orbit the sun. So that tends to make you think about what does it take to actually accomplish that. So let's segue into a much lower TRL discussion. I'll talk about two things. A little bit about the idea of a space warp, and then we'll talk about a form of electric propulsion. You might have seen in the news, we're working on at JSC called QED Thrusters, and so we'll talk to you guys a little bit about that and some of the data we presented at the Joint Propulsion Conference in Ohio. So when we talk about interstellar spaceflight, a lot of people really have no grasp on how far these distances are compared to what we can do today. So I think in terms of state-of-the-art, the Voyager 1 spacecraft is a really good illustration of the best that we've done so far in terms of an interstellar mission. So the Voyager 1 spacecraft was launched in the late 70s. It gave us all those really nice pictures of the outer planets in the solar system that kind of inspired us. It's been on its way for about 30 years. It's moving at about 3.6 AU per year, and AU is the distance from the Earth to the Sun. It's currently at about 120 astronomical units out into the solar system. So we could ask the question, how long would it take Voyager 1 to make it to our nearest star if it happened to be going in the right direction? It turns out it's not. Alpha Centauri is almost due south from the planet. But if it happened to be pointed in the right direction, how long would it take for it to get to Alpha Centauri? It turns out it would take a ridiculously long period of time, 75,000 years. And so I don't know about you guys, that's a really long time to sit on COMSOL. But anyway, it really does highlight the fact that interstellar distances are very, very difficult compared to anything that we've done or ever thought about doing. To kind of continue to highlight the challenges associated with interstellar spaceflight, I want to talk about a project that was convened by the British Interplanetary Society back in the 70s to look at going to Barnard Star that's about 6 light years away. And they wanted to get there in 50 years. The spacecraft that they developed as part of that study using, I think this was pulsed fusion propulsion. The spacecraft they developed and published in their paper was pretty big, around 54,000 metric tons. And you kind of see a photo there that compares the Daedalus to the Saturn V rocket to scale. And I've also interposed a picture of the International Space Station as a comparison. And so I sat on COMSOL for almost all the missions that built the International Space Station, and it took all the resources of all the major spacefaring nations over 10 years to assemble the space station, and that's only 450 tons. So that's over 100 times more mass than an International Space Station. So interstellar flight is extremely difficult and can be a very time-consuming pursuit. So you could ask the question, what if you wanted to get somewhere very quickly? What if you wanted to try and cover that distance from Alpha Centauri in some time period that's not measured in decades, centuries, or millennia? What if you wanted to make it in less than 4 years? It turns out that the same framework that establishes the speed limit, the cosmic speed limit, you cannot exceed the speed of light. There are 2 loopholes within the mathematics of general relativity that potentially allow you to go somewhere very quickly without locally leaving your local light cone. One is the idea of a wormhole. The other is the idea of a space warp. And I'll talk a little bit about that. So the idea of a space warp works on the principle that you can expand and contract space at any speed. It's not restricted to c. We know that inflation occurs in nature when we look at light that comes to us from stars that are in galaxies very far away from us. That light has been redshifted since the Big Bang 13.7 billion years ago. So we know that inflation is a real phenomena, and it's part of general relativity. And so nature can do it. Can we do it in some purposeful way? And so it was this idea that motivated Miguel Alcubierre to publish a paper in the 90s that kind of captured this idea in mathematics. And you see the concept here on the screen. And so when you look at the math and you try and envision what it might require, you see a little surface plot there that represents the expansion and contraction of space. Space is contracting here in the front of the spacecraft, and space is expanding here in the back. When you look at the energy density term, you end up with a spacecraft that has this donut type of apparatus that surrounds this little football shape spacecraft. And so the football shape might be where you'd have your sensitive instrumentation or any payload that you're very worried about. Or if you wanted to be bold, maybe some type of a human crew. Now the metric had a lot of good appealing characteristics when you think about the idea. At that little center area, that blue disk you see on the screen, it has a couple of good characteristics for the concept of a mission like this. It has the divergence of phi is 0, so it has flat space-time inside of the bubble. The coordinate time is equal to proper time inside of that flat region. So the mission control clocks would be synchronized with the clocks on board of the spacecraft. Then the proper acceleration alpha in the bubble is formally 0. So when you turned on the space warp system, the whole crew would not feel an infinite acceleration and go smacking against the bulkhead and killing everybody on board and making for a very sad episode of Star Trek. Now, it does have one unappealing characteristic. After Miguel published his paper and people went to go try and figure out how much stuff would it take to make this concept work, because it requires exotic matter or negative vacuum energy. And so they did some calculations to figure out what would you need to make some type of a system that we would think about actually work. And so the best estimates that were done prior to 2011 were done by some colleagues of mine, Dr. Richard Abusi, Dr. Jerry Cleaver. They reduced the amount of stuff that's required to something that's about the size of Jupiter. And so that's just quite impractical. And so the concept was really considered, maybe nature can do it on a grand scale, but it's unlikely that we could ever do something like this in a purposeful sense. And so I got asked to come to the 100-Year Starship Symposium and give a little bit of a talk on the concept of a space warp. As a result of Pete Worden and some others kind of being visionary and asking for folks to kind of think about this, rather than just kind of relay everything that had been done before by myself and others, I decided to do a sensitivity analysis. I wanted to look at what happens to the mathematics when I change some of the input parameters. And so I looked at and focused on, in this case, the shell thickness parameter. And so you see a couple of stills there from some videos we'll look at in just a second. So this is for a 10-meter diameter spacecraft with an effective velocity of 10 c. And the only thing I'm changing is the shell thickness parameter. So instead of having that football with the ring that goes around it, instead of that ring being a thin aspect ratio, say like a wedding band, if I change it where it looks more like a lifesaver or an inner tube, I can greatly change the magnitude of the York time. And to kind of put that in engineering parlance, kind of like a strain rate, so to speak, on space-time. And when you look at the energy density associated with that, the energy density changes significantly. So just show you some of the animations to help you see. As the thickness of the bubble gets thicker because the ring is getting thicker, the magnitude of the York time decreases significantly. And similarly for the energy density, for that same set of cases, the energy density collapses many orders of magnitude. So what's potentially going on with this finding is that by changing the strain rate that we're having to put on space-time, we're changing how much energy is required to achieve that strain rate. So if I were to, this podium is made out of wood, and so it's about, 3/4 of an inch thick. If I were to try and take my thumb and my forefinger and compress the wood, again using an engineering example, compress the wood by 1/4 inch, Although I'm from Texas, I can't do that. Maybe Pete can. But it's beyond my capacity. But if I reduce the strain that I have to put on the wood to maybe just a nanometer or two, then maybe I can do that. So that's kind of what you're seeing there, is by changing the strain rate for the same case, we are reducing the energy that's required. Now, going back just to point something out here, you're sacrificing some real estate in the center of the bubble. So you see the little flat island where those ideal conditions are is changing its overall size. So it is a little bit of a trade. How much volume do you need to house whatever you're trying to do in some fictional spacecraft? Now, space-time is pretty stiff. This wood is a fairly stiff material. If I could change the material properties and make the wood seem more like a foam, then for the same strain rate, I can further reduce the amount of energy that's necessary to induce the amount of strain on that piece of material. So the question that I looked at next is there something that we can do to try and look at this term that's in the Einstein tensor and the energy density tensor. And so what I did next was look at expanding the Alcubierre metric into a higher dimensional manifold. And so I looked at the Chung-Freeze metric and did some work with some of the null-like geodesics between the two models and found that if you were to go through and vary the intensity in the ring, you can change the stiffness properties of space and potentially further reduce the amount of stuff that's necessary to maybe make this concept work. So I culminated the effort with a table that kind of looked at this 10-meter diameter spacecraft, varying the shell thickness parameter and the time varying potential dphi-dt. And I wanted to duplicate the work done by Richard Debussy and Jerry Cleavers. So I set the parameters such that I could require a Jupiter amount of exotic matter up here. So you can see on the bottom there's some little cartoons that show the relative aspect ratio of the ring relative to the little log scale here. And as you get further to the left, the ring is getting infinitely thin. And so we can, for this 10-meter diameter spacecraft with an effective velocity of 10 c, I can yield the solution that requires a Jupiter amount of exotic matter. I could formally drive it to infinity. But by using these optimization techniques, we can reduce it non-trivially to, in this case, something about the size of the Voyager 1 spacecraft in terms of the effective mass of what you need to make the trick work. So what this does is it moves the idea from the category of completely impossible to maybe plausible. It doesn't say anything about feasible. So unfortunately that point usually gets missed a lot, but at least opens up the door that maybe it's interesting to go try and perform some small experiments to try and see if we can create some type of changes in optical properties in a very small scale in the laboratory. And so that's some of the stuff we're kind of rolling the rock down the road with at our lab at JSC. And so we've got two apparatuses that we use. We have a Twyman Green interferometer. And so this is where we have a test article that we put on one of the reference legs of the interferometer, and we can energize the test article to try and create a blue, in this case with our low fidelity test articles, create a blue shifted frame relative to the lab and change the perceived path length for the photons that move through this region on the interferometer. And so there'll be a slight change in the interference pattern on the interferometer that we can try and detect using some of the software analysis techniques and maybe see if we can't see a manifestation of this in a very small sense. This shows a picture of one of the test setups on the Twyman Green. See the test article there on one of the beam paths. You've got the laser on the left. It's a very standard setup for a Twyman Green. We've got the detector on the right that goes through the computer that collects the data for the data runs. And then the other test setup that we have is a slightly different permutation on an interferometer. We have a FabryPerot interferometer. And so the advantage of a FabryPerot interferometer over a Twyman Green is that you can pass a light beam through a particular region of interest many, many times. And so that increases the measured magnitude of the effect by a couple of orders of magnitude. So it's a way to take a test implementation and get a little bit higher level of fidelity. And so you can see on the bottom two pictures there's an example of a sodium source being run through a Michelson-Morley type of interferometer. You can see the interference pattern. But in the FabryPerot, because of these multiple constructive and destructive interference passes, you start to see the atomic structure of the sodium source, and so you see the doublet in the FabryPerot. And so you see a test setup there with the laser and the imager, and then the FabryPerot that's in the region where we're trying to induce the blue shifted frame with the low fidelity test article. Now, in the process of doing the test, we do turn the test article on and off with a given frequency, and we go through and you see an image on the top right that shows an interference pattern from the imager, and we'll go through and run a test cycle where we run it over an extended period of time, and then we will do an FFT for each and every pixel, and then we will look for energy in the spectrum based on how we were energizing and de-energizing the test article. And you see on the bottom right, that is an FFT of the entire imager at the frequency of interest. If there were no phenomena present, then in principle that should just simply be a flat blue surface. We shouldn't see anything there. However, there are still, when you're working with stuff of this magnitude, there are still false positives, so we would by no means consider this definitive. This is just interesting, and we're continuing to try and eliminate other sources of false positives. Now we have, there's a lab at JSC that was built for the Apollo program, working with inertial measurement units. We were able to get a little small footprint in that lab to be able to do some work and take advantage of the seismic isolation that it has. You can see the big pneumatic piers that floats the entire floor. It's a pretty sizable lab, probably about 30 feet by 40 feet, something like that. And so we can float the whole lab when we're doing testing. And although the lab without being floated is pretty seismically quiet, floating it does make a difference. I will say this, when we first brought the lab out of retirement, the floating the lab out of retirement, we climbed down into the area there where you see the gentleman underneath the floor. We found a couple of suitcases of luggage down there, and we were a little nervous when we pulled those up, when we opened those, what might be in those, but there was nothing in them, so it was nothing exciting. So anyway, this shows an interference pattern with the lab isolated and the lab not isolated in terms of that floating lab. So it does make a little bit of difference in the quality of the data that we collect, but we do have both options open depending upon how much time we have before we run a campaign to get the center folks out to float the floor. I will say this, the floor had not been floated in such a long period of time that apparently they had changed the doors, and when we floated the floor the first time, it actually locked us in the room because it floated up above where the doors couldn't open. So that was, anyway. So the next thing we've been doing is trying to get away from an encapsulated FabryPerot and go to an OpenAir Edelon set of mirrors where we position the mirrors basically in the same orientation that they were inside of the encapsulated FabryPerot, just trying to go through and address some sources of mimicry to make sure is the signal still there? Can we kill the signal or attribute it to some boring explanation? And so we went through the process of taking a look at testing with an OpenAir Edelon, and we still see some energy in the spectrum where we would anticipate to see it. But again, this is definitely not definitive by any stretch. Another way to test at some point to maybe also address other sources of mimicry would be a time-of-flight approach where we could take a helium neon laser and we could run it through an optical chopper that would create light pulses that we could then send through this racetrack and go through and time how long it takes for a photon to run through the test apparatus with a test device not energized. and then time how long it takes for a photon to run through the test apparatus with the device off or on, back and forth, and compare the two. And that can be a different way of detecting the phenomena that if you saw some data that looked like what you wanted on this apparatus, if you didn't see commensurate behavior here, that might be a way for you to say it's some other boring explanation. Now, the one thing that, to me, everyone always thinks about the romantic vision on the right, in terms of being on the bridge of some spaceship going off to destinations very, very far away. And I think that's important, and it is something that kind of motivates us in some way. But I also look at how do we, what do we do to get out of low Earth orbit? What do we need to do to support an asteroid mission in a distant retrograde orbit? What do we need to do to get out to Mars? And so in terms of interstellar precursors, we only have a spacecraft at 120 AU. So while I talked about 10C for some of the stuff I did for the calculations, what about 0.01C? That's a significantly lower velocity compared to that, but compared to anything we've done to date, that's unbelievably fast. So that may still have some interest at some point if we could ever start to mature this past just the concept in a lab perspective. So, if we were to ever to move things forward, that's something to me that I think there'd be plenty of interesting applications with speeds like that. So. Now this is a kind of like an education outreach piece that I did with some folks from CBS. I worked with Mike Okuda and Mark Rademacher. The concept you see here is based on some artwork that Matt Jeffries did back in the 60s for the TV show. He's the guy that kind of came up with the familiar sombrero look that we all know from the TV show. And so he had another version that he generated that I think was one of his favorite. And so this is a modern rendering done by Mark Rademacher based on that artistic concept that he developed. Now the thing that's cool to me is, just going through the math with you guys, you can see that this concept is, it's got some things that are almost what the mathematics requires. It's got these rings that go around the spacecraft, and it's got this centrally located spacecraft. But it does have a few things that are not correct based on the energy optimization findings and where the warp bubble would actually be. The rings on the spacecraft are too thin, so they're going to drive the energy requirements to be non-trivial. So you'd want the rings to be a little different. And then the central portion of the spacecraft is not located properly, and so when the bubble were to form, it would actually cut the bridge off the spacecraft, and the bridge would float away, and Scotty'd probably be fired. So I worked with the guys to kind of upgrade this concept with the mathematics, and so we did an education outreach for like a Ships of the Line calendar where we had a little paragraph that reminded people we're still in low Earth orbit, we've got a lot of work to go do. If this is interesting to you, there's plenty of other work that we need to work on, so please follow your passion and work on science, technology, engineering, and mathematics. But the concept's got these much thicker rings, so it's considerably more athletic looking. Then the little spaceship is kind of more properly located within what would be called the Fenning region. So it's in that little flat space-time, so things would be a little bit better for the crew. Now as we move forward, what we want to do is we want to move to a higher fidelity test article. So you see a concept we're still working on right now in terms of some of the analysis. We want to explore the dphi-dt dependency. Remember I said that was one of the two energy optimization techniques. And so we want to go through and explore the dphi-dt dependency. And some of the stuff that we're doing with the QED Thruster technology has some potential pertinence to this. And so we're using the physics models for that to kind of guide the construction and development of a test article to go through and see if we can explore a much larger magnitude of dphi-dt. And you kind of see a little cartoon of some of the modes we're looking at and some of the specific details we're looking at to put on the inside of the test apparatus. So that takes me through to the next one. That's kind of the interstellar portion of the talk. I want to switch gears now and talk a little bit about the technology that we're working on that's a little bit higher in TRL potentially, a concept called QED Thrusters. And I want to talk about some of the data that I presented at the Joint Propulsion Conference several weeks ago. So a QED thruster is a form of electric propulsion analogous to a Hall thruster. So it's low thrust. It uses electric and magnetic fields to work with charged particles. In this case, we're working on the quantum vacuum, the virtual electrons and positrons, pushing them in one direction, and the QED thruster recoils in the other direction to conserve momentum. So a classical analogy to think about with this concept is to imagine a submarine that has a propeller on the back. A submarine does not go to all the trouble to pull up to a dock and fill up a tank full of water and then expel that water through a nozzle in the back of the submarine. It capitalizes on the fact that it's embedded in its propellant. So the propellant is all around it in the form of the seawater. So it uses the propeller on the back of the submarine to generate a hydrodynamic pressure gradient in the water. And so the water moves in one direction and the submarine moves in the other. So analogously, a QED thruster is pushing off the quantum vacuum, pushing the quantum particles in one direction, and in order to conserve momentum, the QED thruster moves in the other direction. I like this quote from Arthur C. Clarke. This was done in 1980, so back when I was in middle school. If vacuum fluctuations can be harnessed for propulsion by anyone besides science fiction writers, purely engineering problems of interstellar flight would be solved. But I'd also be keen to use it for Mars missions as well. This shows our test apparatus that we use to measure and quantify the force for the test articles. This is a low thrust torsion pendulum. It has all the similar elements that you would find in the other high fidelity torsion pendulums that are used by the agency in academia and industry. On the left over here, you see these things called linear flexure bearings. So these are these two little boxes right here. This is the actual bar of the torsion pendulum that moves horizontally this way. We do not have any cables across the interface. The interface is a cable-free interface. We use liquid metal contacts with a liquid gallon stand. So we pass DC power, digital and analog data across the interface. We do not pass RF across the interface. We actually have you'll see in a minute, the RF sources are actually on the torsion pendulum. We have the ability to test down to vacuum to a few microtorr. And then this is our in terms of measuring and quantifying the force, this is the electrostatic fin system that we use to input a calibration force. So we would put in a voltage of 100, 300 volts. And the benefit of using electrostatic fins, it's a non-contact way to input a force into the torsion pendulum. The advantage of using the electrostatic fins is that the force is constant whether you're 90% engaged or 10% engaged, which is why it's used in this particular apparatus. So when you turn on the calibration force, it stays constant. And then we measure displacement using this optical displacement sensor here. And so this measures displacement as a function of time. And then that way we can input a calibration force. We can test some test apparatus. And then we can quantify what type of force was present when we tested the test apparatus. And then we have a magnetic damper here that converts rotational energy into heat energy. So one of the tests that we did back in August, we partnered with QED to test a RF test article that they were keen to explore some dependency on generating thrust with the presence of some of these radial grooves that go around the periphery of the thruster. So you see, this is a picture of the thruster here. This is a kind of like an imaginary cut through the center of that thruster. And so these radial grooves would be in the periphery of this body of the thruster. This is the RF power input, and this is the sense antenna. So the QED folks felt there might be some dependency on the presence of the slots in the test article. So we asked them to bring a slotted test article and a non-slotted test article. So this goes through and shows testing some of the test articles on the torsion pendulum. You've got a picture there. There's a block diagram that shows the test article. We've got the voltage-controlled oscillator, the variable voltage attenuator going into the dual directional coupler, and we measure the forward and reflected power on the torsion pendulum. And then we use a whip antenna through one of the glass ports in the vacuum chamber for real-time tuning. This shows a typical data run. This is the optical displacement sensor. We would put in a calibration pulse for some period of time, turn off the calibration pulse, energize the test article for 30, 60, 90 seconds, turn that off, and then run another calibration pulse. And that would be considered a data run for the test article. We took some infrared imagery of the test article on the torsion pendulum to try and understand what type of heat the system generated. It's a high Q resonance system, so the test article is not going to generate a significant amount of heat. Most of the heat was in the heat sink for the RF amplifier, and we always kept the amplifier below 100 degrees Fahrenheit. We didn't want to get it over 100 degrees Fahrenheit. So you just kind of see the breakdown of the temperature there. It's about 85 degrees on the amplifier. This shows a synopsis of the test results with the QED test article. We tested each test article in a forward and reverse sense. So you see in the pictures there with the thrust going to the left in the picture and the thrust going to the right. Basically, we flipped the test article. All the other supporting elements were kept in the same orientation. On the back of the torsion pendulum, as I noted, the RF amplifier served as the counterbalance for the test article that's on the front of the torsion pendulum. And we only piped across DC power and digital and analog data across the interface. So for the slotted test article, the average thrust was around 40 micronewtons in the forward direction and about 49 micronewtons in the reverse direction. The unslotted also generated thrust in the forward and reverse direction, about 41 and 23 micronewtons. We did test a RF dummy load where we would take off the test article and put the dummy load on the torsion pendulum and energize the system and run all the RF drive electronics at full power. And that generated no detectable thrust with this configuration. So there was no other systemic dependencies with the RF equipment. Now, we did some work in COMSOL to try and understand what was happening with the electromagnetic fields in the thruster. And we looked at the RF feed system for the test articles. The RF feed systems had a dielectric slug inside as part of the matching network, a dielectric slug of PTFE. When we looked at the electric and magnetic fields in that region, there was a net pointing vector, and so we speculated that that might be a quarter wave, a resonance system that might be exhibiting some Q thruster physics. So we took the COMSOL analysis results and we plugged them into our analytical Q thruster model. And based on the as-tested conditions for 25 watts with a quality factor of 8,000, it predicted a potentially observed thrust of 34 micronewtons. That's not definitive, but it's at least within an order of magnitude. So it was interesting to us, and that might explain why the slotted and the unslotted both generated thrust. To us, from the Q thruster perspective, the big bell there is just simply a matching network to establish the right conditions in that quarter wave resonance system that you see there on the right. So we also looked at another topology. So we explored a tapered thruster approach based on some work done by Northwest Polytechnic University. See you in Houston, Pete. We optimized the construction and the location of the dielectric in the antennas using COMSOL and the Q thruster physics to try and understand, can we develop something that within 25 to 30 watts can generate forces that we can clearly see on the torsion pendulum. So in the process of doing that, when you deal with a tapered system, there's a lot of different modes that you can exhibit in a tapered system. So we used COMSOL to generate all the predicted network parameters when we use a vector network analyzer to go through and take a look at the as-built system and compare it to the theoretical system to make sure we're exciting the particular modes that we want to excite. And so you see a snapshot of the analysis compared to the output from the vector network analyzer. The one thing I will highlight is these types of situations are a little problematic from a tuning perspective. That's where you have potentially two modes in very close proximity to one another. And so if you try and couple to one of those two modes, it can make tuning a little difficult, and you can bounce back and forth between modes, and that can be a little challenging when you're trying to gather data. This shows the test article loaded on the torsion pendulum. On the bottom left there, you see the test article. The RF amplifier is on the far right. It goes to the dual directional coupler where we measure the power forward and power reflected. It goes through some shielded cabling into the test article. We did go through and measure all of the leaking RF fields. The system was very RF quiet. All the leaking fields were less than what a cell phone would put out. So we had a very clean RF system. Let's go into the data. I think I'm running a little low on time here. This shows us testing at the TE012 mode using the COMSOL analysis. It predicted a quality factor of 22,000 or 21,800 compared to the 22,000 observed. We were able to get about 2.6 watts of power into the test article in this configuration. With the COMSOL analysis of the QED thruster physics, it predicted a thrust magnitude of about 50 micronewtons. We measured just a little over 55. You see a thrust run up there in the inset with a calibration pulse energizing the thruster. And then another calibration pulse. And then you see the COMSOL analysis of the field conditions on the top right. And then again, another picture of the test article on the torsion pendulum end on. The TE012 mode had, it was in one of those areas where we had another mode in very close proximity. So that made operation of that mode difficult. So we switched to the TM211 mode. There's actually two of them about a few megahertz from one another. And so we investigated the TM211 mode, the first one and the second one. For the first mode, the as-tested quality factor was just a little over 7,000. We were able to get a little bit more power into the test article, just about 17 watts. The peak thrust that we observed was a little higher, 116 micronewtons. The average thrust was about 91 micronewtons. When we did the null force test, we measured a 9.6 micronewton null force. That's again with that RF load brick that we showed you with the QED test article. The COMSOL analysis predicted a quality factor of just a little under 8,000, and with an input power of 17 watts, it predicted an observed thrust of 313 micronewtons. So we're a little off by about a factor of 3 with that particular mode. And this goes through and shows some of the data runs for the TM211 mode. You see the calibration pulse, and then turning the RF amplifier on, doing a little bit of manual tuning. You can also see when you're getting into the 100 micronewtons, it's the comparison to the calibration pulse, it's starting to be pretty large. This shows the null test, putting the RF load on there, just to go through and see what type of systemic sources of error we might have. And so that goes through and shows you that just a little over 9 micronewtons of force as a result of the maybe tied to the 5.6 amps that went to the RF amplifier. We also tested at the second TM211 mode. This one was a better RF mode, but it was a less capable QED thruster mode based on the analysis and what we saw with the data. So the as-tested quality factor was 18,100 versus the about 8,000 for the previous TM211 mode. About the same power level. The net average thrust we picked up with this particular mode was just about 50 micronewtons. And the COMSOL analysis for the TM211 does predict it is a better RF system at 32,000 quality factor. And with an input power of 16, just a little under 17 watts, correcting for the difference in the as-built quality factor versus the theoretical, we're predicting a thrust of around 47 micronewtons. So what we found from this is that there does seem to be two different sets of optimization dials we have to try and further explore. One has to do with RF optimization, and the other has to do with the Q thruster physics, and they don't necessarily have the same dependencies. We did find that having a dielectric in the tapered portion of the thruster was extremely important on the magnitude of the thrust. We saw that both in the analysis and in the test, because we did test the TE012 mode with no dielectric present in the thruster, and it did not generate any force to within the resolution level of the torsion pendulum up to 30 watts, which also matched the predicted performance. Now the NPU work that was done here in the last year, they published some results. They've worked in much higher power levels than we have. I think we'd like to continue to work in the low power. Our torsion pendulum really helps us kind of explore the basics. But they did explore 80 watts up to 2.5 kilowatts, considerably more force up to the hundreds of millinewtons, with a thrust to power that was a little bit higher than anything we've worked with, up to 1 newton per kilowatt. They used an inverted pendulum thrust stand, kind of a standard design approach where it uses null displacement. So you see this is the inverted pendulum thrust stand right here, and it uses these coils to hold the inverted pendulum at the zero displacement used based on the feedback from this sensor system. And that's how they go through and measure and characterize force. In this case, this is the test article. The microwave would be down here. It would come in through a circulator. This is a load over here, and then it would go up here and energize the system. And this goes through and shows their work they did with the 80 to 1.2 kilowatts. And they've got up to 0.9 newtons per kilowatt. And then they also did work in with another magnetron design that went up to 2.5 kilowatts. And again, they saw considerably higher forces than anything we've looked at. Again, we're content to work at the low power for now. In terms of the value proposition, with some of the experience we've seen with these things, a lot of people always want to know, this is interesting and fine, but what does it look like if you try and apply it to an application? And so if you've got a system that's capable of generating 0.4 newtons per kilowatt, it's certainly not going to lift itself off the ground, but it is potentially a useful in-space propulsion system. And so we looked at what happens if you have 0.4 newtons per kilowatt with some type of a stack that's in a distant retrograde orbit around the moon. So this is kind of linking back to the asteroid mission. And so you've got some stack mass that's about the right mass for some type of aggregate of modules that we might use in human spaceflight. But we're constrained with only 300 kilowatts of solar power. So in terms of the things that we have on the horizon, that's one of the constraints that we have to really salute. We're not going to be given very big arrays that have huge values associated with them. 300 kilowatts is a very realistic constraint that we need to try and work with and try and do the most we can with what we've got. So in this case, with a 70-ton stack departing from a distant retrograde orbit with 300 kilowatts of solar power, we can go to a 50-day mission around Deimos and get back to Earth in 788 days. The other thing we did was we constrained it so that you would not go in Venus's orbit. And so in order to kind of match the planetary billiards, the spacecraft swings out to 2AU to try and wait for Earth to get into a more favorable alignment, kind of like a high yo-yo maneuver for the pilots that are in the group. Now, if we ever did have some type of a consistent power source that were up to a couple of megawatts, I looked at what could you do with 0.4 newtons per kilowatt. with 2 megawatts of power for a 90-ton spacecraft. Out of that, 50 tons would be cargo, 20 tons would be allocated to the nuclear reactor, so it's about 10 kilograms per kilowatt. For folks that are familiar with reactors we've looked at in the past, we're not trying to be overly aggressive in terms of what the reactor would have to be in terms of the specific mass. And then 10 kilograms per kilowatt for the Q thruster, so that's about twice what you'd do for a Hall thruster, so we tried to be just a little sloppy with that. You get a little bit different look and feel than what we saw in the previous slide. The previous slide looks more like a traditional low thrust mission. But what happens here is that the thrust to mass for the spacecraft actually breaks 0.6 milli-Gs. So when you're in heliocentric space at 1 AU, 0.6 milli-Gs is the attraction to the sun. So what happens is if you have any spacecraft of any kind with power and electric propulsion, if it can exceed that 0.6 milli-Gs, then you might be able to do interesting things like that. So independent of the Q thrusters, that's just an interesting metric that we found in the process of exploring that. I think I'm running really low on time, so let me just pop through to the plan forward. So moving forward, we want to implement a phase lock loop that prevents us, that precludes us from having to do manual tuning. We can basically have almost light switch like reliability. We want to be able to gather a larger amount of data over multiple operating conditions. We want to do some power scanning. We want to continue to evaluate some different RF modes and explore some different antenna configurations. And then the test system that we have now, the amplifier that we procured, has the ability to be tested at vacuum, and so that's our next step. And then instead of doing a test with an RF dummy load, we want to perform future null tests with the thruster actually rotated orthogonal to the thrust axis. So we want to leave the thruster on the torsion pendulum, test in one direction, the other direction, and then rotate it where it's orthogonal to the thrust vector. And then once we've pounded all that flat, we've been talking with Glenn Research Center about doing some independent verification and validation. In their vacuum chamber, they have a low thrust torsion pendulum that we can utilize to go through and explore what it does in that facility. Then Johns Hopkins has also talked about doing some type of a Cavendish balance test with the IV and V ship set. So I think with that, I'm just about almost up to my time. So there you go, I'll hand it over to questions.
Video you wanted to show as well? Okay, questions, everybody?
Thank you for coming here.
Yes, sir.
I have a hypothetical for you.
Yes,
if
sir.
you had an unlimited budget and a mission to get yourself to Alpha Centauri and had to choose between an Alcubierre type warp drive and a antimatter drive that would be, of course, subluminal, which would you think would be the more practical choice?
That's a great question. I'm going to answer your question. I'm not going to pick a horse. I would probably do both from the standpoint. If I had the unlimited budget that you're talking about, I would like to have multiple paths to maybe increase the likelihood of success.
Okay, let me frame it. You only get to pick one.
I only get to pick one. I don't know that I'm prepared to answer that. If you have an unlimited budget and you want to come back and tell me, then I'll make a decision, right? So, yes, I guess. Oh, yeah.
Thank you. Maybe I missed it. What exactly physical phenomenon are you measuring with your interferometers, and what results would you consider as positive or negative? So could you explain this a little bit?
You're asking what are we trying to measure?
With interferometers.
In the interferometer.
Yeah.
We're trying to change the optical path length in a very small region of the interferometer by having the appropriate conditions with what the general relativity requires. And then it says in a local region, it'll change the perceived path length for the photon line integrals. So then that'll manifest itself in the form of a slight change of the interference pattern. I mean, not something you're going to see with the naked eye. It requires computers to see.
Thank you.
Yeah, sorry, he's got the microphone.
Since I got the mic, Creon,
He's got
could I, regarding the Q thruster, Could I get you to address this whole conservation of momentum question?
Absolutely, yeah. So the Q thruster does conserve momentum if it works as we think it does based on the physics. If you're pushing off the quantum vacuum, you're establishing an anisotropic state in the quantum vacuum, and so it is putting a wake out of the back of the thruster. And at some point, if we continue to see good data and we rule out all other false positives, one of the things we would like to go through and explore is what is the momentum distribution and what's the divergence angle of the wake. And so we would do that by using another Q thruster that would kind of recouple with the wake in the quantum vacuum and try and measure the wake.
Okay. Oh, wait. Could you do causality on the other one, too?
Causality.
Oh, on the warp drive. How do you avoid causality violation, or does it happen?
You never locally exceed the speed of light, so you can't do any. I like Dr. Hugh as much as the next guy, but you can't. There's no time travel possible with the space warp. Kriyan.
Thanks. The Alcubierre warp metric and other ones require exotic matter. How, and so I presume if you're trying to make some kind of Alcubierre thing on the optical bench with this interferometer, are you trying to make exotic matter in your test article, which you didn't say very much about?
Yeah,
or
so
what's going on with that test article,
Yeah.
and why should it be an Alcubierre-like effect?
Yeah, so the low fidelity test article is trying to create a blue shifted frame relative to the lab. So we're just using a large potential energy with our low fidelity test articles. The higher fidelity test article that I showed you guys a picture of, that is based on the Q thruster physics, and so that's where we go through and we work on using the negative vacuum energy to try and satisfy all the explicit requirements of the field equations. So that test article is trying to establish more accurately the requirements as set up by the mathematics, working with negative vacuum energy, Casimir force.
Am I off? Okay, but maybe we could take this offline if it's too technical, but E fields, B fields, the kind of things you get inside of a resonant cavity or with capacitors and coils are all, then none of those are exotic matter. Those are all just standard mass energy, not the kind that you need for the Alcubierre metric, which has the opposite sign, which no one knows how to make.
Let me answer your question. Right, so we had some of this discussion actually yesterday in your office. We were talking about some of the Q thruster physics. So in terms of the Q thruster physics, we're not just looking at classical E&M. We're talking about what that potentially does in the quantum vacuum based on the physics models associated with the Q thruster physics. So with the Q thruster physics, it potentially provides a connection to a perturbed state in the quantum vacuum. So yes, just the pure E&M fields by the classical sense, they're really not of interest. What's of interest of us is what does that mean when we look at it from the Q thruster physics perspective. So that's the only reason why there's interest in that.
Okay, so let me see if I understand this. If you just had the E and B fields, you would expect no exotic effect. But if you have these dielectrics or whatever inside of it so that you're getting this strong coupling, then maybe you would see an exotic effect?
You made too strong of a statement. I think that there's, in the process of exploring what Q thruster physics means for the magnitude of E and B fields and how that might be coupled to what's potentially going on in the quantum vacuum. In principle, right, you have to have the right conditions to get the magnitude of an effect that you can measure. But you were too general with your statement, so I can't agree with you completely with that. Anyway.
Okay, thank you.
So we have one more question here.
Okay.
This is very, can you hear me? This is very non-technical, more of a popular science magazine type question for you, so be ambiguous if you want to. But assuming that all your measurements are not dominated by systematic noises that you might not have realized at this point, assuming that all these measurements are correct. Sorry?
I didn't hear that last part.
Oh, assuming that all these measurements are correct, that they're not dominated by noise that you haven't accounted for. Yeah. And in a fictional world where you will have funding to continue pursuing this at a comfortable level for the next 20 years. Where do you envision this technology to be in 20 years' time? Is this something that we'll be able to use to send satellites to other planets?
That's a big question. I don't have a good answer for you. Certainly you'd like to make a lot of progress, but I mean, there's no shortcuts, right? You know, it's definitely crawl, walk, run. We'll try and make as much progress as we can within the resources that we have, and basically the data is really going to drive that discussion, right? I mean, you know, in God we trust, everybody else bring data. So data is really going to drive that discussion. So I'm sorry, it's not like, you know, I can't give you a good, quick answer, but just there's no shortcuts, right? So.
I told you it could be ambiguous. It's fine.
Okay, please join me in thanking Dr. White.